Hello, this is Mr. Benner, and I'm going to talk you through polarity and how you can tell if molecules are polar or not. Okay, so polar molecules have regions where they have partial charges, and you might remember the charges are positive and negative. Now, they're not quite ionic because ionic compounds have separated positive and negative charges. Polar covalent bonds just have partial charges on different parts of the molecule. So like, maybe the oxygen atoms and the carbon dioxide are a little bit negative and the carbon atoms just a little bit positive. And you can see that's here because the carbon atom has a lower electronegativity, much lower than the oxygen atom. So carbon's at 2.5, oxygen's at 3.5. So oxygen pulls the electron density away toward itself, so does the one on the other side. Now, overall, these are equally and oppositely directed dipoles. So overall, this molecule of carbon dioxide is nonpolar. Now, there are some circumstances where, say it's in water, it is able to weakly attract to the water because the water molecules are small enough to come along beside of it and exploit the fact that there's low electron density or a slightly positive charge here in the middle where the carbon is, and the oxygen is slightly negative. But overall, this molecule is considered to be nonpolar, and it's pretty non-soluble in water, and you know that because anytime you've ever cracked open the lid on a soda can, you know that the carbon dioxide starts bubbling right on out of the water. Now, oh, I thought I clicked on it. Okay, here we go. Right now, molecules that are polar, so these bond dipoles, you're able to determine the overall dipole moment or the overall polarity of a molecule by adding these bond dipoles together. So notice that over here, if you added this one, which is negative, and that one, which is positive, they point in opposite directions, so they cancel out. If you added these together, they both point upward a little bit, while one points to the upward to the right, the other points upward to the left. So the right and left parts cancel out, but the upward part remains. So the overall dipole moment of this molecule, which by the way is water, points up toward the oxygen. And that means this part of the molecule is slightly negative, and then this part of the molecule is slightly positive, again because of these differences in electronegativity between these different atoms. Now, let's see. So we'll look at some different molecules here, and they tell you HCl is polar. The electronegativity difference, or the electronegativity value, is given here, so you can see 2.1 and 3.0. So that is a difference of 0.9. That's less than 1.7, so it's still a covalent bond, but it's more than 0.3, so it's a polar covalent bond. Some molecules have polar bonds in them, like BF3 is a very polar bond, but notice that all of the fluorine molecules are spread out evenly around the boron. That makes it have three-dimensional symmetry, and so overall this molecule is nonpolar, though the bonds are polar. Same thing with CCl4. There's a polar bond between the carbon and the chlorine. However, there's three-dimensional symmetry in this molecule that helps it be nonpolar. Ammonia and CH3Cl, I believe that's chloroform. It might be chloroform is CCl3 or CHCl3, but anyways, somewhere in that department. So this is a polar molecule because these dipole moments point toward each other, and that part cancels out, but the fact that they all point upward a little bit makes the ammonia or the nitrogen side of the molecule be slightly negative, and the hydrogen side of the molecule be slightly positive. Same thing happens down here with the CH3Cl, and the chlorine is the most electronegative, so it attracts electrons up toward it. The chlorine is partially negative, the remainder of the molecule is partially positive. Now, what you need to do, draw the Lewis structure, draw the, or determine the shape of the molecule, and then here are some guidelines that will help you through this. So molecules are usually polar if you have a molecule that has two atoms and they're different. So an example of that is HCl. If you have a central atom that has a lone pair, so ammonia, NH3 is an example of that. That one was here. It's not drawn on here, but there would be a lone pair up here that's influencing the shape. So usually when there's a lone pair on the central atom, the molecule is polar. If the central atom has bonds to different types of atoms, so the example here is the CHCl3, nonpolar molecules, all the diatomic molecules, if all the bonds are the same, it's going to be a nonpolar molecule. And then if the central atom has bonds to all the same, by the way, this is different, diatomic or all the same atom, that's different than the central atom having bonds to all the same type of atoms. So the central atom and the terminal atoms can be different, but as long as it's all bonds and no lone pairs, usually that's going to be three-dimensional symmetry and nonpolar. Alright, also carbon-hydrogen bonds are usually nonpolar. In fact, it's very rare for those to be considered polar. If you're paying attention and you're like, hey, wait, Mr. Benner, I thought if the electronegativity difference was 0.3 or greater, then the bond was polar covalent. And you're looking at carbon and hydrogen, you're like, oh, carbon's 2.5, hydrogen's 2.1. A lot of periodic tables look like this. And if you subtract those, you're like, hey, the difference is 0.4. That's supposed to be polar covalent. Well, sort of. Okay, if you look to one more significant figure, the electronegativity of hydrogen is 2.20, carbon is 2.50. That's a difference of 0.35. So that's really stinking close to 0.3, and then usually there's more than one hydrogen atom bonded to a carbon, and usually the way they arrange themselves, it makes them less polar. So long story short is simply that carbon-hydrogen bonds, they're pretty much nonpolar, and you can just go with that. Now, let's look at some sample molecules here to talk about polarity. So I've got this thing set up to show you the bond dipole right now, and that shows this side is the part that's positive, this side is the part that's negative. Notice that right now I've got this set up so the atom A has low electronegativity, atom B has really high electronegativity. And I'm going to go through and show you the partial charges. Notice that as these get closer in electronegativity to each other, the bond dipole and the partial charges go away. Now, if we talk about the bond character, right now we've got a really low electronegativity, that would be like francium, and then a really high electronegativity like fluorine. That makes a really ionic bond. So if you're to bring these where they're closer in electronegativity, then you have a more covalent bond. Somewhere in the middle might be a polar covalent, and then eventually you get over to an ionic bond. Now, let's take a look. I'll show you the potential. So what they're showing you with this electrostatic potential is that the blue side is more positive, the red side is more negative. And notice the atom with the greater electronegativity is colored red here. The one with the greater or the lesser electronegativity is colored blue, and that's because the one with greater electronegativity attracts electrons to itself while it's bonded. The electron density map shows the darker side where the negative is at because there's more electrons there. Now, let's think I've explored that enough. Now, things get a little more complicated when you deal with 3 different atoms, and also depending on how they're arranged in 3-dimensional space, but I'll leave them like this for now. And if you've got, this is a fairly common arrangement for B and C to have lower electronegativity, and then or excuse me, A and C to have lower electronegativity, and then B to have a little bit more. This is kind of like a water molecule. So you can see the individual, the bond dipoles, they point toward the more electronegative atom, and then the partial charges. So the more electronegative atom has a partial negative charge, and the less electronegative atoms have partial positive charges. And the more electronegative that central atom gets, the larger those partial charges get. Alright, now let's look at some real molecules. So we've got, I'll show the bond dipole on this. So hydrogen is it has a very low electronegativity, or relatively low electronegativity. Fluorine's very high, so this is a very polar bond. In this one, the dipole of the molecule and the bond dipole match because it's a linear molecule. There's only 2 in it. And then you can see the partial charge here. Fluorine's partially negative, hydrogen's partially positive. And let's do that potential map. So this side of the molecule, red means negative, blue means positive. And there's electron density. Okay, let's look at some diatomic molecules. Notice that there's no bond dipole on these. There's no partial charges. There's no potential difference or difference in electron density with all of these diatomic molecules. We've already looked at HF. Let's look at water. Okay, so you can see that oxygen has a large electronegativity compared to hydrogen, and then the bond dipoles point from the hydrogen to the oxygen because the oxygen's better at attracting electrons, and then those bond dipoles combine together to give this molecule overall a dipole that points from the positive side where the hydrogens are at to the negative side where the oxygen is at. There's carbon dioxide. Does have bond dipoles, but notice that there's really no molecular dipole. So remember, I told you that this molecule is nonpolar overall. There's the electron density. You can tell there's a little more out here, but where the oxygens are at, but overall that molecule is nonpolar. Okay, hydrogen cyanide. Okay, and that's a linear molecule. Whoa. You can see that, and overall the nitrogen side is negative and the hydrogen side is positive. Let's look at ammonia because that's a really common molecule. Let me take some of the stuff off. Okay, so remember we did the shape of this molecule. It's a trigonal pyramidal shape, and the bond dipoles all point from hydrogen to nitrogen, and all together that makes a molecular dipole that points straight up if you pretend that the hydrogens are on the floor or on the ground and the nitrogen is all, elevated. So those all combine. So that means that the nitrogen side of this molecule is negative and the hydrogen side of this molecule is positive. And that polarity makes for some interesting properties. It causes the molecules of ammonia to be able to stick to each other and also to other polar substances like water. Thanks for watching.